All right. So now I want to take another look at a flux integral and see if I can estimate the flux of a vector field through a surface in the same way that I can estimate the work integration over a curve. In some cases, not in all cases, but in some cases. So, for example, if the vector field looks like this, perhaps. Here's a particular vector field that goes around in a circle, like this. And I have a curve like so that is following this circle, oriented perhaps like this. Then we know that the integral over f, integral of this closed curve C of the vector field f, which is the one that goes in a circle here as well, is going to be what? Well, I know that I'm not having to exert any work here. I'm going to get work back if I follow this. So this means that I'm going to get work back. So this is going to be positive. All right, so now I want to see if I can do this similar, if I can make a similar argument for finding out whether the flux integration is positive or negative. So let's start with the vector field. Now in this case, I'll make a simple vector field like this. So my simple vector field looks like this. There are always arrows pointing to the right, let's say, like so. All right. And they're all of equal length, perhaps, or in fact, what I'll do is I'm going to make them such that they're all of equal length, perhaps. Like this. And I'm going to put in two surfaces now. One surface is going to go like this. Let's make it green. So surface 1 is like this. This is a projection in 2 dimensions. So there is really a 3-dimensional surface. The vector field is 3-dimensional too. It goes like this. Here the surface. So there's my surface S1, let's say. And let's find my surface S2 to be this one. Like this. This is my surface S2. I want to figure out what's the integral over the vector field. What's the flux of the vector field F over the surface S? This is F dot n ds, surface S1. And what is the flux over the surface S2? F dot n ds. Now, in both cases of my surfaces here, S1 and S2, I can fairly easily find the normal vector that I need, because the normal vector to the green surface, the S1 surface, the normal vectors would look like this. They would be parallel to the vectors of my vector field, like this. All right, so that means that, remember that, of course, the dot product goes like this. We know for the dot product that A dot E is equal to the length of A times the length of B times the cosine of the angle between them. That's good old stuff from way back when. Therefore, if these vectors of the vector field and of the normal are parallel, means the cosine, the angle is 0, means the cosine is 1, means the dot product is as big as it can be in this case, and it's going to be positive because both vectors point in the same direction, so this is going to be a positive number, so that means the vector field is going to be positive. The flux is going to be positive because f dot n is going to be positive, and I have then the positive thing here with the ds integration that can only be positive. On S2, on the other hand, my normal vectors look like this. The normal vectors point up always, and therefore the dot product of the normal vectors, the blue ones are my normal vectors now of the surface S2. Now the blue ones are perpendicular to the vector field vectors. That means that the dot product here, this dot product, is going to be 0, which means that the flux over the surface S2 is going to be equal to 0. And that makes sense if you think about it, because if the surface is like this, then there is nothing flowing through the surface. Everything flows. The surface is very thin, let's say. Nothing flows through the surface. Whereas if I put the surface perpendicular like S1, then the flow through the surface S is going to be maximum because all the flow vectors are going to be parallel to the normal vectors here of the surface. All right. So with a little bit of imagination, for certain easy vector fields, I can estimate the flux vector, the flux just fine. All right. So that's the estimation of the flux vector. Thank you.